Welcome back. Most of the algorithms discussed so far arose out of statistics. The support vector machine is an invention purely from computer science. Vladimir Vapnik developed the ideas for the support vector machine in his PhD thesis in the 1960s in his native Russia. Unfortunately, the computing power was not present at the time to implement the algorithm. Later, Vapnik immigrated to the U.S. to work for Bell Labs. He submitted several papers to top conferences, but his papers were rejected. Vapnik's persistence paid off. He went on to win numerous awards, including the 2017 IEEE von Neumann Medal. The key ideas are summarized in this figure, where we see two classes, represented by red triangles and blue dots, divided by a separating hyperplane, represented by the orange line. Although visualized in two dimensions, representing the two predictors x1 and x2, we should think of the separating line as being a hyperplane in multidimensional space, for the more common case when we have many predictors. Notice that the separating line has margins on either side, the dotted lines. The goal is to find margins that separate the classes, and the margins should not be any wider or narrower than necessary. We also see instances actually on the margin, here, here, and here. These are called the support vectors from which the algorithm gets its name. Classification then would simply be a matter of determining which side of the margin an instance falls on, designated by class +1 and class -1. Standard SVM uses a linear decision boundary. The orthogonal vector W here, the vector of the weights, points to the positive class. The margin is perpendicular distance from the decision boundary to the support vectors on either side. Here we see two green support vectors, and here's another support vector. Then the classification rule for a new observation coming in is going to be +1 or -1, which we can combine into one equation here. This equation will equal 0 for the support vectors. The width of the margin is the difference of two support vectors on different margins, normalized by the unit vector of W. The margins have width 1 minus b, so if we add these we get 2, and this is the function here that we want to minimize. This function to minimize is constrained by the support vectors, which are those observations that equal 0 in this formula. Lagrangian multipliers, shown in this equation by the alphas, allow us to put together optimization expression and constraints. To find W, we take the partial derivative with respect to W and set it to 0. Alpha will be non-zero for support vectors. And then we find B by taking the partial derivative of the equation with respect to B. Once we plug it in, we get this rather unwieldy looking equation here, which can be simplified here. The point to take away is that this is going to be a quadratic optimization problem of the dot products of the pairs of samples. This is computationally expensive in training, but once the support vectors are determined, all other observations are irrelevant and only the support vectors remain for classification. An important concept is slack variables. The idea is to let a few observations be on the wrong side of the margin, or if within the margins. A C hyperparameter will control how much slack is allowed. Larger C values will result in larger margins and more support vectors. Smaller values of C will have lower bias but higher variance. Optimal values of C are tuned using a validation set. Because a linear classifier may not be able to classify data, you can't draw a linear line anywhere here that would separate the two classes. What we can do is map the observations into a higher dimensional space, and then use a polynomial kernel to separate the observations. Another option is the radial kernel. In this case, we'll have an additional hyperparameter of gamma, which is going to be tuned on the validation data. Larger gammas can overfit, leading to a model with high variance, and smaller gammas can underfit, leading to a model with high bias. The term hyperparameter is used to refer to a parameter for the algorithm, not of the data. We're going to use linear SVM on the iris dataset. So first we load the data and then do a train test split. An SVM implementation is in library E1071. We specify our formula, our data, and that we want a linear kernel. This cost parameter is the C hyperparameter that we talked about, how much slack variable we're going to allow. And you can optionally scale the data. We see that we ended up with 15 support vectors for the 3 classes. In this case, we got an accuracy of 100%. Here we can get a visualization of what it learned. For the 3 classes, we see a few misclassified observations. Next, let's look at a regression example. Next, we're going to do SVM regression on the Boston housing dataset that's in library Mass. Once again, using library E1071 for the SVM implementation. I'm going to need a validation set. Here I'm showing one way to do this. This code is in the book. An alternative way would be to first sample your training indications and then resample the training indications and use a portion of those for validation set. I end up with 303 observations for training, 102 in validation, and 101 in test. As a baseline, I'm trying linear regression on the dataset, getting a correlation of 0.845 and a mean squared error of 21. First, I'll try a linear SVM, and we see that the correlation is slightly lower and the MSE is slightly higher. There's a built-in tune function to tune the hyperparameters for cost. So I'm giving it a range of values of C to try, and then we'll tune it. From that tuning, we can pick out the best model with this code and use that on the test data. We see even with tuning, we didn't get very good results. Correlation is lower, MSE is higher. Our results on the polynomial kernel are promising. We get the highest correlation so far of 0.89 and a much lower MSE of about 15.7. Let's try a radial kernel, just arbitrarily picking some values for cost and gamma. And that didn't do as well as the one that was tuned, so that means we probably need to tune these hyperparameters. And it still didn't get quite as good result as we got with the tuning of the polynomial. We see that the correlation here for the tuned radial kernel is fairly competitive with the tuned polynomial kernel, and it's a little bit less competitive here in the MSE. In this data, the best results were achieved by a polynomial kernel tuned with the validation data. Because only a few instances determine the margins, SVM is robust to observations that are far from the hyperplane. In other words, it's robust to outliers. SVM classifiers have this in common with logistic regression. Logistic regression and SVM often give similar results. If the classes are well separated, SVM tends to perform better than logistic regression. Some of the advantages of SVM are that it can be used for both regression and classification, and the choice of kernel, linear, polynomial, or radial, makes it a very versatile algorithm. It is, however, computationally complex, and you have to do a lot of tuning on the hyperparameters to get best results. There's a lot of new terminology in this chapter, listed here at the end of the chapter, And also we have listed for quick reference how to do regression or classification. The algorithm will figure it out based on the target type. Here's some sample code that will give you a train, test, and validation set. And here's an example of how to tune a linear and a radial kernel and to output the best model for predictions.